Hello there. In this video we're going to continue our discussion on looking for all of the zeros of a polynomial function p of x. We're going to restrict our discussion from the fundamental theorem of algebra to the set of rational numbers and discuss a particular theorem known as the rational zeros theorem. Alright, so to begin, let us first briefly go over what the fundamental theorem of algebra said, which some people abbreviate just by FTA. So it says that this polynomial, and let's assume without loss of generality that the leading coefficient is 1, that this polynomial always factors completely over the set of complex numbers. In particular, there are numbers x1, x2, x3, all the way up to xn in the set of complex numbers, such that this polynomial factors into x minus x1, x minus x2, x minus x3, all the way down to x minus xm. Let us assume that we expand using the distributive property this product expression. So if we multiply the first terms together, then there's going to be x times x times x times all of those x's, and namely there's n terms here, so this is going to expand into x to the power of m, plus then we're going to have some function of x in the middle whose degree is going to be n minus 1, and then at the very end we're going to have the product of these coefficients x1, x2, x3 all the way down to xn. And that could be positive or negative. It depends on the signs of these xk's. So I'm just going to write that as plus or minus x1 times x2 times x3 times xm. So these are going to be the products of these zeros. Now notice that this does not have an x term associated to it, so this actually corresponds to the y-intercept. So this is the y-intercept, because when we plug in 0 into p of x, p of 0 is going to be 0 to the n plus f of 0. And we know that this function evaluates to 0 because all of these terms has x in them, namely x to the n minus 1 all the way down to just x. So both of those are going to go to 0. So therefore this is the value of the y-intercept, namely 0 comma this number. So the constant in the expanded polynomial will tell you the product of the possible zeros in this case. And most of the time we represent this y-intercept as just a0. So let us assume that a0 was equal to 6. Now what are all the possible ways for which we could product into this number just over the sets of integers? Well, we know that the factors of 6 are going to be equal to, so I'm going to just represent this as f of 6 for the factors of 6. So that's going to be equal to plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And this product, x1 through xn, could be any combination of these numbers. It really depends on what the degree of this function is, because you can have 1 times 6, or 2 times 3, or 2 times 1 times 3, or 6 times 1 times negative 1 times 1 times negative 1, or any combination that sort of gives you a constant coefficient of 6. So now, with these preliminary things, let us first state what the rational zeros theorem says. So let us suppose that P is a polynomial, and let us assume that it has real constant coefficients, and let us assume that P of 0 is equal to a0. So this is going to be equal to our y-intercept constant. And let us assume without loss of generality then that the leading coefficient of P is equal to 1. Then the possible rational zeros of P are all of the factors of A0. And we pretty much did a quick sketch of the proof right above with that fundamental theorem of algebra expansion. Now, of course, we can bypass this special case that the leading coefficient be 1. We'll consider that in the follow-up video to this. But let's assume, just for simplicity purposes for this discussion, that the leading coefficient is 1. So let us look at our first example. Let's assume we have f of x is equal to x cubed minus 2x squared plus 3x plus 1. Now, there are infinitely many numbers which we could plug into this and see if it gives us 0 or not. But what the rational zeros theorem does is it gives us a finite and hopefully small set of numbers that we only need to consider. So the number that we're going to be focusing on here is 1. So the factors of 1 are just going to be 1 and its opposite, -1. So those are the only two rational numbers, in this case it's just an integer, that we need to consider. So let's try 1 and let's try -1. And I'm going to use synthetic division since it tends to be a little bit more quick compared to long division. Alright, so 1 comes down, so that's 1, -1, -1, 2, 2, and 3. And then we have 1, -1, -3, 3, 6, -6, -5. So as we see that neither of these are equal to 0, that means 1 and -1 are not zeros, which means x minus 1 and x plus 1 are not factors of this. So therefore, there are not rational zeros for f. So what does this mean? So overall, we know that the degree of this polynomial f is equal to 3. And clearly there's not 3 zeros for this case. So from the fundamental theorem of algebra, we know that there are 3 zeros in C for which we're looking for, and we know from the fundamental theorem of algebra that they're not in Q. So if that is the case, then that means this C, these 3 zeros, could come in one of a few ways. So you could have, say, I don't know, 2 complex zeros. Remember, complex zeros come in pairs if the coefficients are real. So 2 complex and 1 irrational. Now I'm not going to discuss what it means or what type of number this irrational number is. Like, is it a square root? Is it a cube root? Is it like pi or e or something like that? I'm not going to go into the details of that because that's definitely a little bit more advanced. So it could have 3 zeros in C, so it could be 2 complex, 1 irrational, or all 3 of them could be like irrational or complex or something like that. But nonetheless, we know they're not rational, so we do not need to continue trying to guess numbers. And then maybe we need to do like a numerical method to try and see what these numbers might be equal to. So let's look at another example. Let's look at g of x is equal to x cubed minus 2x squared minus 3x plus 6. So now we have a constant coefficient of 6. So the factors of 6 are going to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Therefore, the set of numbers that we need to consider is 8 of them. It's 4 of these factors and their opposites. So if we try all these 8 and none of them work, that means all of them are either irrational or complex. Alright, so let's start with the easiest ones, plus or minus 1. So I'm going to do 1, so 1 minus 2 minus 3, 6, and minus 1. 1 minus 2 minus 3, and 6. So this is going to give me what? So 1, 1, minus 1, minus 1, minus 4, and 2. Let's see, 1, minus 1, minus 3, 3, 0, minus 1, 5. All right, so we've tested 1 and negative 1, and neither of them work. So let's move on to 2 and negative 2. So being comfortable with synthetic division definitely will save you a lot of time. All right, so let's bring down 1. So we're going to get 2, 0, 2, minus 1, minus 2, 4, 1, minus 2, minus 4, 8, 5, minus 10, minus 4. Let's see, wait a minute. Something's off. Oh, 2. So 2 times 1 is 2. That's 0. 2 times 0 is, oh, that's 0. So that's a little bit off. So 2 times 0 is 0. That's going to be minus 3, minus 6, 0. Ah, there we go. That's better. So now we see that 2 is a 0 for a polynomial. So what does that mean? So that means our function g of x is going to be equal to x minus 2. Remember, if 2 is a 0, x minus 2 is a factor. And this is going to be our quadratic to be considered. So we can have x squared plus 0x minus 3. So if we were to try 3, negative 3, 6, and negative 6, you would see that synthetically you will not get a remainder of 0 because you can see that neither of them correspond to this factor. So that means we have one rational 0 and the other two are either complex or irrational. Now in this particular case we can find the other two because this is a difference of squares, a difference of irrational squares, namely x plus the square root of 3 and x minus the square root of 3. But that gives you just an introduction to the rational zeros theorem. In the next video, we'll look at a couple more examples where the leading coefficient is not equal to 1.